Alright everyone, so welcome back to my channel. So today I'm gonna go through problems called shortest path to get on the key. First of all, you are given an m by n grid, and the dot is an empty cell, the hashtag is a wall, the a sign is the starting point, the lowercase letter represent the key, and the uppercase letter represent the lock. So right here, as you can see, this is an example. This is the empty cell, so you can see this is the dot right here. The a sign is the human, key is, let's say, letter A. This one is probably letter A uppercase. It is the same, and this is like that. So you're at a starting point. You can move 4 directions. So this one can go up, down, right, left. And you cannot walk outside the grid, and you walk into the wall. So if you face a wall, you cannot do that. You can just go straight, go to this side. If you walk over a key, you can pick it up, and you cannot walk over a lock unless you have the corresponding key. So let's say if I walk on this key A, I need to somehow store this key A in my pocket, right? And whenever I come down here, go to my right, oh, I have the B, but I don't have this key, so I cannot walk to that. I have to go to the right. So I do have key A, so I can walk on this, and then I move on. I take this key B, I add to my pocket. Then from this key B, I walk back to this. From this key B, I already have 2 key, so that is where we return our result. Key. This means that exact case letter, first K letter of the English alphabet. So first K letter, and for some 1 to 6. So they're only A, B, C, D, E, F. And this means that there's exactly 1 key to each lock, and there's U's represent the lock chosen by alphabet. If it is impossible, we return -1. That makes sense. And then return the lowest number of move to acquire on key. So in order to have a lowest number of move to acquire on key, the first thing you need to think of is BFS, and because this is a grid, right? And you're just simply using a BFS function. The condition to escape these BFS loop is when you have on key, then you have A and B in your pocket, or you out of move, so you move on away for some reason, you don't have any more, you cannot move left, right, down anymore, and your queue is empty, right? So that was when you escape the loop and you return -1. If you have the key, you will return the count, so you just simply add a count into the queue. 2. So that is our regular BFS function. The one thing that is makes this problem a little bit tricky is a little bit tricky is how you have a pocket. You can use an array size of 6 to hold key like this. You can use that. Let's say you will have an array size of 6, right? From 0 to 6 right here, and it's contained false for all the key, right? Something like that. And if you found a key A, you convert that to 0. You make this true, right? Make this true. And whenever you find you on A right here, you convert that to lowercase. You change that to 0, and then you check if that is true in our pocket of 6. Yep, something like that. And we have to, since this one is BFS traverse, and it have a state which is our pocket like this, we will have to add this whole pocket into a right with our row and column and pocket, whatever it is, right? But this is not really, this is good enough, but it's not really efficient, because whenever you add a new pocket, right, into a queue or into a visit, you have to make a copy of it, right? So that is when it make these not really efficient, because you have to make a copy of an array of 6 for every single step that you are moving. So that is not really great. Instead, we use something called Bitmask. So Bitmask. Imagine you got an empty pocket with size 6 like this, right? Same, it's gonna be an array, but it is represent in an integer, in a bitmap integer, right? In here, let's say you found key A. The key A represent 0 index, right? So it's gonna be our first index right here. If we do this operation, so 1, we shift to, let's say A right here is gonna be 0, right? We shift by 0, we will have a bitmask that look like this, 0 1. Let's say we turn this 1 0, right? We have this bitmask, all right? So the way we add to our pocket, which is right here, is we just do a simple OR operation. So or the 1 shift 0, right? Shift to the left by 0. You will have, because this is OR, you will have this, right? So this means we have key A in our pocket, right? So if we have key A right here, right? So then we move to the lock. This lock is B, right? Let me remove this and draw like this. So this is our pocket. We move to B right here. So we convert B to B, we convert that to a number, which is 1, right? If we shift left that by, let me just, hold on, right? By 1, oh, yep, shift by 1. So we will have something that look like this. Oops, not like this. 1 0, right? So we have this is the lock, right? So we'll have to do an operation to check if this is correct, right? So it's gonna be an operation. So this and this is 0, this and this 0 0, right? So this turned out to be 0, which is false. So since it's false, we cannot start doing anything with it. We have to go back to this side where we found a key, this. So this one should be an A 0 0. Oops, this keep happen. So this is an A 0, so we shift by 0, so we have this bitmask, and now our operation work. So 0 0, this is turned to 1, which is true. Let's say, yeah, true, meaning that we can move on, like, right? We can do a quick operation that look like this, right? Just for example, and let's do it like this. Let's say we have something that look like this, right? So this is where we have, for example, we have a C, we converted it to C. It's gonna be 2, right? And then we do have the key at this point, right? So we do an AND operation. 0 0 0 0. This turned out to be 2. This turned out to be 0 1 is 2 over 1 2 2 2's, right? So we multiply all of this is a something. So it's gonna be return an integer, right? And that besides 0 is gonna be true. So this one return true, right? So you know what? Let's just code it up and see how it's going. So first of all, what we're gonna do is we're gonna have our row, column, and which is the length of the grid, right? And then we also have the length of row right here. So if the grid only have what grid is only have one side, like one square, just return 0. So we have our directions right here, which is gonna be 0 1 0 1 1 0 -1 0 and 0 -1, right? We can have our point, which is gonna be 0, right? And our starting column also is gonna be 0. We have our keys we have key amount, so we need to, you know, right? So we need to count it for, yeah, final mask. So go loop through the so and range C. So if the grid row and column go to a sign, so this is starting point, so we set that start point to our row and our start row column into our column if the grid row and column is right. So we're gonna count a key, just count a key, oops, plus is 1, right? So we have our final mask is gonna be 1 shift to the key amount, right? Minus 1. So this one final bit mask is gonna be represent, let's say we have, you know, right? It's gonna be like this 111. It's gonna look like this, right? So this is why I count a key, and this is our final bit mask. If our current bit mask is equal to this amount, we return the count. So we have our initial bit mask, which is gonna be B0000. So this is our 0 in bit mask. So Q is gonna be the Q, right, of visit. So we do visit. So we also need our visit. So now in our queue, we need to append the starting point. So start. We need to add our init bit mask and the current count, right? So just a note right here. We have row, column, mask, and our count, right? So we also need to add to our visit are the starting point, the starting column in init bitmask, right? Okay, that's pretty good so far. We all have like a functions. Let's call character, right? We add our character in here, and then we just return ordinary of the character minus ordinary of the a character. So this return a number. Then we just do a we start gonna do our BFS. So for I in range and then in range of length Q. We have our row column, our mask, and we have our current count, right? Which is Q dot top left. This BFS function will ensure our shortest, you know, number of move that needs to get the key. So for direction row, we have our new row column, which is direction row plus row, and then the direction column. Right. We have a new mask. Go to our mask. Then we are out of bounds. So new row, smaller than 0. We continue. Same thing for the other side. So new row equal to row, or new column equal to the column. We continue. And then if we hit a wall, right, if grid row and column equal to a wall, we continue. And then also we need to update our mask, right? So to update our mask, we need to grid new row, new column if that is lowercase, right? We do our OR operation to update our pocket, our mask, right? So mask OR is the OR operation. One Y. Oh, what am I doing? One value of the grid on grid, and then so now we have our new mask. We need to double check if our new mask is in visit, right? So if new row, new column, and a new mask, let's just make sure that we don't hit come back to the same spot, right? So continue, and then we need to come to find out if we hit a lock, right? So if grid this one, this is upper. So if we hit a lock, what we do is if the log, right, if not mask and 1 bit shift to count value of the, let's do this about that, right? So this one is if we return, let's say if we don't have, if not right here, right? So if we don't have the in our bucket that match with the log, right? So we need to continue, and then if now for the final check, if our new mask, go to our final Bitmask, we can return the current count plus 1, and then after all of this case, we can finally add to our visit what we need to add, right? New row, new column, new mask, and then same thing down here. Q, append, new row, new column, new mask, and a current count plus 1. Okay, if exit the loop, we return -1, meaning that it's impossible to, key. Let's try it. Should for some reason there's no oops, silly mistake. Count val. Oh, it should be count character, not value. So right here, run again, see if it's word. Ordinary string, ordinary a. Okay, but a boolean found. Okay, so this one is lower. It actually should be lower. Yep. Let's try here. Perfect. So the time complexity for this problem is gonna be O of n times m, and the space is gonna be also O of n times m. Yep. And yeah, because we do the Bitmask right here, so that's why the time complexity is so fast. Alright, thank you for watching, and I hope to see you soon on the next video.